Hi, today in 7.4 we're going to be looking at modeling with exponential functions. So a lot of these will be very familiar to you. A lot of them don't even involve derivatives. So first of all, exponential growth. We're going to be looking at exponential growth with base e. So here c is just some constant, and the rate constant is the constant k. Notice if I were to take the derivative of my function y with respect to time, it's the base e exponential function, so stays the same, just times the derivative of the exponent, or just k times y. So we call that derivative the absolute growth rate. But notice, if I were to divide both sides of this equation by my function y, I would be able to isolate k. So k equal to the derivative divided by the function is what we call our relative growth rate. So the general form of our exponential equation is going to be y of t equal to y sub 0 times e to the kt. And here y sub 0 is the initial value when t is equal to 0. And we're going to compare two models in this example. We're going to be comparing linear versus exponential growth. So here, suppose we have the population of town A, which is given by 1200 plus 100t, so notice that's a linear function. And we have the population of town B given by the function 1200 times e to the 0.1t. Okay, so here t is measured in years. And we want to find the growth rates and relative growth rates of the town. So let me look at town A. So the function that models the population for town A was 1200 plus 100t. Okay, so notice when t is equal to 0, the population of the town is 1200. For t greater than 0, the population is going to increase. So if we wanted to compute the growth rate, we would just take the derivative of our function with respect to t, and that's just 100, which means the town's going to grow by 100 people per year. So this is persons per year. And this would be our growth rate. To find the relative growth rate, all we do is take that growth rate and divide it by our function a. So the relative growth rate is equal to 100 over the function, which was 1200 plus 100 times t. Okay, so this would be our relative growth rate. So what this is saying when we look at our growth rate is the population is going to increase by 100 people per year. And that remains constant. Every year the population grows by 100. The relative growth rate is a little bit different. The relative growth rate gives you the percent in the increase in the population year by year. So it's going to change. So for instance, When t is equal to 0, our population is 1200. When t is equal to 1, the population is 1300. When t is equal to 2, the population is 1400, and so on. So when you look at the growth rate here, the increase from 1200 to 1300 would be something like 8.3%. But then from 1300 to 1400, it drops to 7.7%. Okay, so the relative growth rate is the percent increase relative to the year. So now let's look at town B. And remember, the equation for the population at any time was this exponential function. So it's 1200 times e to the 0.1t, or just point t is fine. So if we're figuring out the growth rate, we take the derivative of b with respect to t. And it's an exponential function, so remember it's 1200 stays the same times the derivative of the exponent, which is just 0.1, which would be 120 e to 0.1t. So that's the increase in population per year, or persons per year. So this would be our growth rate. And then our relative growth rate, which is the percent change in the population from year to year, is just our growth rate divided by our function. So it's going to be 120 e to the 0.1t over 1200 e to the 0.1t. So notice that the e to the 0.1t cancels top and bottom, and then I can also reduce my fraction here. I get 1 over 10. And then this would be our relative growth rate. Notice that 1 over 10 is the same as 10%. So what that's saying is that although the growth rate is not constant, our growth rate has an exponential function in here, so that's not a constant number. What is constant is the relative growth rate, 10%. So the population, the change in population year by year is always going to be a 10% change. Okay, so let's go on to another example. We'll go to the next page. And this is some language that you'll see as you go through your Connect Math. It says to devise an exponential growth function that fits the given data and answer the question. Okay, so it's telling you to first find the growth function and then answer the question. So the population of the state of Hawaii was 1.43 million in the year 2016. Assuming an annual growth rate of 1.1% per year, what will the population be in the year 2020? Well, the general form of exponential growth is y to the t equal to y to, sub 0 e to the kt. And here our initial population, y sub 0, is 1.43, and I'm going to leave off the unit millions for now. So plugging that in, we have the population is 1.43 e to the kt. So in order to model this particular problem with a growth function, I need to find k. So something we need to note is that after 1 year, the population has grown by 1.1%. Okay? So if I plug 1 for t in my function, I get 1.43 e to the k, because t is equal to 1. And I also have that after 1 year, my initial population of 1.43 will increase by 1.1% or 0.011 of the initial population. So that means that these two values are the same. So if I set them equal to each other, that will give me one equation with one variable, and I can solve for k. Now I could plug this into a calculator, but we want to use exact answers wherever possible. So in this equation, what I'm going to do is I'm going to go ahead and note that I could factor out the common 1.43 in each term, which will leave me 1 plus 0.011. So now it's just a matter of algebra, or 1.43 times 1.011. Okay. Now when I set those two values equal to each other, I'll have the equation 1.43 e to the k is equal to 1.43 times 1.011. So notice that the 1.43 will cancel on each side. And now if I just take the natural log on both sides, it will enable me to get that k out from the exponent, right? Because of the property that the natural log of e will cancel. And I have my k. K is equal to the natural log of 1.011. And I do not want to approximate that. That is an exact answer. We never round until the very end. So now going back to my original equation that I started with, I can go ahead and substitute for k. My growth function is y of t equal to 1.43 e to the natural log of 1.011 times t. Okay, so now we have our growth function. We want to use this function to answer the question. Okay, so it says assuming an annual growth rate of 1.1%, what will the population be in 2020? Okay, so what we want to do is figure out what t value we're going to put into our function. So the t value we're going to use is the year we started with was 2016. We want to find the population in 2020, so 4 years. So y of 4 is equal to 1.43 e to the natural log of 1.011 times 4. Now we can put this in the calculator, and we'll get approximately 1.49 million. Okay, so in 2020, the population should be approximately, or about, 1.49 million. Okay, so typically we answer word problems with a sentence. Okay, so let's go on to another example. This time we're going to be looking at another type of problem that you should have seen before, and that would be doubling time. So this is a type of exponential growth where what we have, the information we have, is the doubling time. Okay. which is given by this equation here, t sub 2 equal to the natural log of 2 over k. Okay, and the only reason why we have a 2 here is because that stands for double time. Okay, so let's look at our example. Devise the exponential growth function that fits the given data. Okay. The number of cells in a certain type of tumor doubles every 8 weeks, starting with 10 cells. So this is an exponential growth function. It'll take on the form y of t equal to y sub 0 e to the kt. And I know that I'm starting with 10 cells, so that y sub 0 is 10. And I also know what k is. If I take my doubling equation, okay, where t sub 2 is the 8 weeks, so this is our t sub 2, I get k is equal to the natural log of 2 over 8. And this is exact. Remember, we don't want to use a calculator until the very end. So my equation is y of t is equal to 10 times e to the natural log of 2 over 8 times t. So that would be the exponential function that models this particular problem. So after how many weeks does the tumor have 1,600 cells? Okay, so the 1,600 is the population of cells. So I'm going to replace y of t with 1,600. And then I'm going to solve this equation for t. Okay, so the first thing I'm going to do is I'm going to divide both sides by 10 to get 160 equal to e natural log of 2 over 8 times t. So I'm solving for t. The problem is that t is in the exponent. So to get it out from the exponent, I'm going to natural log both sides and get the natural log of 160 is equal to natural log of e natural log of 2 over 8 times t. So again, natural log of e is gone. Okay, so it's just a matter now of multiplying by the reciprocal, 8 over natural log of 2 to get the t by itself. So we get 8 times the natural log of 160 over the natural log of 2 equal to t. Again, this is my exact answer. Once I plug this into a calculator, I get that t is about, and we'll just round this to a whole number, 59 weeks. And typically we would write a sentence answer, but to save on space, I'll just stop there. All right, so now looking at B, it says after how many weeks does the tumor have 3,200 cells? So you would think that if it goes from 1,600 cells to 3,200 cells, that since the cells double, the time doubles, but that's not true because this is not a linear function, this is an exponential function. So in part B, we're going to be setting the population equal to 3,200 and then solving this exponential equation. So this is exactly what we did in part A. We just have 3,200 instead of 1,600. Okay. So we're going to have 320, is equal to e to the natural log of 2 over 8 times t. And then when we take the natural log on both sides, we have the natural log of 320. The e will cancel, and we have natural log of 2 over 8 times t, which is the same as 8 times the natural log of 320 over the natural log of 2. Okay, again, this is our exact answer. If you plug this in a calculator, you should get approximately 67 weeks. So although the cells doubled, the time did not, again, because this is an exponential function. And again, I would actually have a sentence answer if this were, if you were showing your work on an exam. Okay, so let's look at one last example. Instead of something that grows, what if we have decay? Okay. So exponential decay, notice that the exponent has a negative in it because it's decreasing. Now typically with decay, we have what's called a half-life. And in the half-life, you notice the subscript is half for half-life. Makes sense. So the half-life of Xanax in the bloodstream is 11 hours. Okay. Suppose a patient receives an initial dosage of 6 milligrams at 8 a.m. The question is, how much Xanax is in the patient's bloodstream at 10 p.m.? Well, first of all, I'm going to need to model my problem with this exponential decay. And hopefully I can figure out what k and y sub 0 are. Well, I know that my initial population is 6 milligrams. Okay. And I also have 11 hours for half-life. So my equation becomes y of t is equal to 6 e to the, oh, but what is k? Okay. K is equal to natural log of 2 over half-life is 11. So e to the negative natural log of 2 over 11 times t. So almost exactly like our previous problem. Okay, we have our model. Now in part A, we need to figure out how much Xanax is in the patient's bloodstream at 10 p.m. So we have to figure out what T is. So we started at 8 a.m. 10 p.m. means that T is 14 hours. So y of 14 is equal to 6 times e to the negative natural log of 2 over 11 times 14. So this is just a calculator problem. Once you put it in your calculator, you'll get approximately, and I'll round it to, no, I think I'll go 1 decimal, 2.5 milligrams. Again, that would be in a sentence, right? Okay, so B says, when will the amount of Xanax reach 10% of the original dosage? Okay, I have the original dosage, so what this is saying in part B is when means we're trying to solve for time, and we know that this has to equal 10% of the original dosage. So it's going to be equal to 0.1 of the original dosage, which is 6 milligrams, equal to 6 e to the negative natural log of 2 over 11 times 14. Okay, so that's nice because I can divide both sides by 6. And then I just realized what I did. Did you see what I did? I put 14 here for some bizarre reason when it should be T. I apologize. So solving for t, we have natural log on both sides, negative natural log of 2 times 11t. So it's okay to skip that step where you show natural log of e and then cancel it. So it's just a matter of multiplying both sides by the reciprocal of negative natural log of 2 over 11 to get negative 11 natural log of 0.1 over natural log of 2 equal to t, which is our exact solution. When we put this in the calculator, our t value will be approximately 36.5 hours. Again, that would be in a sentence. Okay. So let's look at C. When will the amount of Xanax reach 5% of the original dosage? So 5% of our original dosage, which is 6 milligrams, that's what we're going to set our equation equal to. And this is all the exact same as what we did before. We're just changing some constants. So I am going to skip some steps. Sixes cancel, natural log both sides, and we have the natural log of 0.05 is equal to the negative natural log of 2 over 11t, but if I multiply by the reciprocal, I get my t value, which is about 47.5 hours. All right, and then the last piece, which I think I am going to squish in here, would be D. Oops. When will the amount of Xanax reach 1% of the original dosage? So again, exact same thing as we did before, but it's 0.01. So 6e to the negative natural log of 2 over 11t. And that turns into natural log of 0.01. Remember the 6's canceled, and then we would multiply by the reciprocal, so negative 11 over natural log of 2 is our t, and t is approximately 73 hours. Okay, and that's it for this section.